Alrighty, so let's have look at a few examples over here involving Eulerian and Hamiltonian graphs. Alright, so question one, so I just got my working out already on there. For the graph shown below, name a path starting at F and ending at F. You do not visit vertices more than once. So a nice simple one from A to B to D to F. From A to B to D to F. Didn't say I had to hit all of the vertices. Doesn't say anything about Hamiltonian, Eulerian, any of that stuff. All it said was get a path from A to F, as long as I don't hit any vertice more than once. A to B to D to F. Nice and simple for that one. Alrighty, next one. Name a Hamiltonian path starting at A and finishing at F. Now, Hamiltonian means I have to hit every vertice, but the restrictions on this one is I have to start at A and finish at F. So, an example of one is I go from A to E, from E to C, C to B, B to D, and D to F. What that looks like on the graph, I go from A to E, go from E up to C, from C to B, B to D, and from D to F. I started at A, I ended at F, and I hit every vertice along the way. Cool. Question C. Name a Hamiltonian cycle from A. Now, a path, as in question B, started and finished at different vertices. If it's a cycle, it has to end and start at the same vertice. So if it starts at A, it needs to end back at A. And being Hamiltonian, it needs to hit every vertice and repeat 0 edges. Okay, so question C, I can go from A to E, from E to F, F to D, D to C, C to B, and B back to A. How that looks on our graph from A to E, E to F, F to D, D to C, C to B, and B back to A. Didn't repeat any of my edges, and I hit all of the vertices, and I started and finished at A. Remember, with these ones, it's all about trial and error and using a bit of like logic and inspection. So if you don't get it right at first, don't give up, just keep giving it a go, unless you're wasting a heap of time in a test. All right, question D, name a Hamiltonian cycle from D. Naming that one, I go from D to C, C to B, B to A to E, E to F, and F back at D. What that looks like on my cycle here, on my graph, sorry, is D to C, C to B, B to A to E, E to F, and F back to D. Cool. So when you're tackling these types of questions, yes, there's no real easy starting point or anything like that. You just got to pick a vertice that looks like it's going to give you a good shot, and then go from there and trial and error from that one. I would strongly recommend using like a pencil nice and lightly going over it so you can erase it nice and easily if you make any mistakes. All right, so that is example one. All right, so example two, we've got a bit of a diagram of a floor plan here. Model the access to rooms on the first floor of this two-story house as a network diagram. Hint, the rooms are vertices and the doorways are edges. Alrighty, so let's start off by modeling this situation here as a bit of a network. I'm going to do that down, let's say do it down here. Question A. We've got the lounge room, the dining room, the kitchen, the hallway, bedroom 1, the bathroom, bedroom 2, and the veranda. So each of those is a different vertice. All of the doorways, if you're like picturing yourself living and walking through this house, are all of the edges in our network. Okay. So quickly drawing it up on our thing here, the lounge can connect to the dining hall. It can also connect to the hallway. There is no direct connection from the lounge to bedroom 1. It has to go through the hallway. So the direct connections from lounge room is to the dining room and to the hallway. Dining room, then to the hallway. All right. The next one, let's look at the dining room. Connects to the lounge room like stated before. It also connects to the hall. We can also go through this side door here to the kitchen. So the dining room can connect to the hallway and it can connect to the kitchen. To the hallway and to the kitchen here. Let's have a look at the kitchen in a bit more detail now. Yep, it can go back to the dining hall. It can go down and out to the veranda. It can go out into the hallway. So the kitchen can connect to the veranda, the hallway, and as we already know before, it can connect back to the dining room. So it goes from the kitchen to the hallway, dining room, and the veranda. Cool. Next one, let's have a look at bedroom 1. Bedroom 1 can connect to the hallway, and that's it. The only direct connection from bedroom 1 is the hallway. If you're living in this house, you exit out of your bedroom 1, only place you've got there is the hallway. Looking at the bathroom does connect to the hallway. It also connects directly to bedroom 2. Those are the two connections there for the bathroom. Connect to the hallway and it can connect to bedroom 2. Looking at bedroom 2, it connects back to the bathroom and then also to the hallway. Bedroom 2 connects to the hallway and bathroom there. Cool. Question B. Alrighty. Question B. Is it possible to walk through all of the rooms exactly once and return to the room you started in? Justify. Alrighty. So this is pretty much the saying, is there a Hamiltonian cycle? Can I hit every room, every vertex, and end up back at the same room I started at? And after a bit of thinking and stuff, you should hopefully come to the conclusion like, no, there is no Hamiltonian cycle present. And one of the ways to tell this is looking at, get the red one up, is looking at bedroom 1 down here. If I ever want to go into bedroom 1 and then back to the hallway, I've gone to bedroom 1, come back out, I've repeated that edge. Remember, in a Hamiltonian cycle, there are no repeated edges. Another thing, if I go from lounge room, say to the hallway, to bedroom 1, and then back to the hallway, I've used the hallway twice. In a Hamiltonian cycle, I cannot repeat any vertices. So the only way to get in and out of bedroom 1 is to use the hallway vertice twice. So we cannot do that. No, as bedroom 1 has an order of 1. So the hallway must be used twice. The hallway is used twice. There is no Hamiltonian cycle. All right, cool. Let's have a look at example 3 now. All right, so this is our last example to go through for Hamiltonian Eulerian graphs. Consider the graph below. Does the graph have a semi-Eulerian path? If so, find such a path. If not, give a reason. Alrighty, so we've already got the order of each vertex labeled on this graph here. When we're talking about Eulerian graphs, we need to look at the order of each of these vertices. So for it to be semi-Eulerian, remembering from the start of the lesson, it needs to have exactly 2 odd vertices. If we look at our graph here, B and C, they are our two and only two odd vertices. So yes, this graph is semi-Eulerian, which means there will be a semi-Eulerian trail through it. So yes, as there are exactly two odd vertices. Now let's name that path. Now an example of such a path is going from C to D, back to A, to H, to I, to G, to D, to F, to E, to D, to I, to A, back to B, I, C, and then B. Remember, in semi-Eulerian path, if it's to be semi-Eulerian, I need to hit all of the edges, but it does not matter if I repeat vertices. So it's quite a big network. I want to get to all of the vertices. So that is meaning we've got quite a long path going through here. Alrighty, so what this path looks like in our network is I'm starting at C. Now, a good idea, what I generally try to do is look at the odd vertices and try to start from there. It generally helps me. If that doesn't work, just pick another vertice that you think looks good and try and find a path from there. So I need to hit all the vertices. Doesn't matter if I repeat the edges for a semi-Eulerian path here. So I'm starting at C, I head to D, and then I head directly to A. So I follow this arcy one over here. From A, I'm then going down to H, to I, down to G, from G back to D, D down to F, F to E, E back to D. From D, I'm heading to I, from I to A to B, back down to I, up to C, and then across to B and finishing up there. Hit all the vertices, hit all the edges, repeated vertices where I needed to. Key thing with the Eulerian is I hit all of the edges exactly once. Alrighty, let's have a look at our next question here. Question B. Does the graph have an Eulerian trail? If so, find such a cycle. If not, give a reason. Alrighty, well, we've already established it's semi-Eulerian, so that should give you the answer for this one already. The answer is no, it is not Eulerian. No, and the reason is as there are more than zero odd vertices. Remember, for it to be Eulerian, it needs to have zero odd vertices. We have more than zero, so it is in fact not Eulerian. It is semi-Eulerian. Question C. Does the graph have a Hamiltonian path? And if so, find such a path. Now, unfortunately, there are no hard and fast rules on like our Eulerian. Like mentioned before, we just have to guess and check and have a couple of goes at it, see what works. Turns out, yes, there is a Hamiltonian path. Remember, if it's a Hamiltonian path, it means it is a semi-Hamiltonian graph. Semi-Hamiltonian graph has a Hamiltonian path, which means I hit all of the vertices, but I don't necessarily start and end at the same vertice. So the answer is yes. I do have that one there. And this is an example of such a path. Going from F to E to D, from D to G, G to I to H, H to A to B, and B to C. What that looks like on my network here is I start at F, head to E, I go across to D, from D I go down to G, G to I to H, H up to A to B, B to C, and I've hit all of the vertices, haven't repeated any edges, anything like that, hit all the vertices exactly once, Alright, with this last one, with question D, after some trial and error, you'll find that no, it does not contain a Hamiltonian cycle. Alrighty, that's all the examples. Thanks for listening.